Hello, everyone. This is part two of chapter 13, the second part of gravity. Um, Today, we're going to talk about a few problems in gravity. We're also going to talk about what we do when we need to handle gravity in the middle of the Earth, something under the surface, let's say. We're going to talk about how to understand the energy in satellite motion, and then we're going to talk a little bit about escape velocity for different particles, specifically why planets like Jupiter retain their hydrogen, but the Earth really doesn't. Then we'll be done. A lot of math today, a couple of good examples. So let's get started. All right. So last time, when we talked about Kepler's laws of planetary orbits, these apply to all bodies in the solar system, and one really well-known object is Halley's Comet. Halley's Comet has been seen since since as far back as Romans, early Chinese, a lot of the early Middle Eastern civilizations knew about Halley's Comet. It comes every 75.3 years, and I believe the last time it was here was in 86. So it's supposed to come back soon in your lifetime. You'll probably only be able to see it once in your lifetime. But if Halley's Comet has a period of 75.3 years, and we know that the distance of closest approach is 0.586 AU, so a little over half the distance from the sun to the Earth is the closest it gets to our sun. And we know that it has a maximum velocity when it gets there of 55 times 10 to the third meter per second. We want to know a few things. We want to know what its eccentricity is. We want to know what its speed is, how far away it gets. So we're going to want to know. I should also say that our first step here is this is T. This is actually our perihelion distance, and this is our velocity of perihelion. We know that it has a maximum velocity of at perihelion because if it's in elliptical orbit, remember, it's doing something like this. And at perihelion, it's going to be going faster. That's what Kepler's second law, equal area and equal time, told us. So we want to know VA. We want to know RA. This is RP. And we want to know what its eccentricity is. So another thing to note is that we have our period in years and our radial distance in AU. Okay? All right. So if we go back and remember, Kepler's first law was that objects orbited in ellipses, and that gave us the following equations. If this is some center, this is A, so 2A was equal to RP plus RA. And I should say that we are looking for A, VA, and E, and RA. Okay. All right. So 2A is equal to RP plus RA. We also know that from here to here, let me call these just perihelion and aphelion, because that's what they are. So this is A, and no, it's not. This is P, and this is A. Perihelion, this is aphelion. We know that this is EA, and this is RP, so A has to equal RP plus the eccentricity times the semi-major axis. And we know from Newton's third law that T squared is equal to 4 pi squared over G times the mass of what you're rotating. Halley's Comet is rotating about the sun times the semi-major axis cubed. And the last thing, Kepler's second law gave us that RABA is equal to RPBP. Okay, so let's find the eccentricity first. From this equation, actually we need to find A first. From this equation, remember that if we are in our solar system, as long as T is in, Earth years, so if T is in Earth years and A is in AU, we don't have to use that extra stuff. Kepler's third law tells us this is true if T is in Earth years and A is in AU. So let's find A. If T is 75.3 years, we get that 75.3 squared is equal to A to the third. This tells us that A is equal to what's called the third root of 75.3 squared. And that answer is 17.8 AU. So this is 17.8 AU, which seems correct from the internet, of all things. Okay, so we now know the semi-major axis of Halley's Comet. That means this distance to the center is 17.83 AU, or almost 18 times the distance from the Earth to the Sun, the average distance. The next thing that we need to know is VA, okay? We should actually skip down and just find RA first. So we know that RA plus RP has to equal 2A, or that RA is 2A minus RP, and RP was 0.586. So this is 2 times 17.83 minus 0.586 AU, which is 35.08-ish. So about 35.08 AU. Remember, you could turn this into meters if you wanted to, because 1 AU is equal to about 1.5 times 10 to the 11th meters. The Halley's Comet is at its furthest distance away, RA, is 35 AU. Essentially, Neptune is at 30 AU, and Pluto's at somewhere like 39. So Halley's Comet, when it goes out past Neptune and almost to where Pluto is before it turns around and comes back in. And it takes 75.3 years to do that. The next thing we wanted was the eccentricity of this orbit. And we know that RP plus EA is equal to A. Therefore, RP is equal to A minus EA, or solving this for E, actually, we get that EA is equal to A minus RP. Dividing through by A, we get that E is equal to 1 minus RP over A, which is pretty easy to see. 1 minus 0.586 over 35.08. And this eccentricity is going to be really big. 0.586 divided by 35.08. I get 98. I believe the actual number for Halley's Comet is given as 90.967. I'm getting 983. Probably rounding issue, But this eccentricity here, so we found A was 35 AU, E was 0.983, and A was 17.83. So this orbit is almost parabolic. It's almost equal to 1, which means it's almost an open object or an open orbit. So that means that we have A and RA and E, okay, 17.83, 35, 17.83 AU, about 35 AU, and about 0.983. So it's got some extremely thin orbit as it comes in. And we know that it's almost out past, it is past Neptune. It's almost out to Jupiter, okay? And the last thing that we want to know is when it gets way out here by Jupiter, what is its velocity? So we know that RP VP is equal to RA VA. That was Kepler's second law, or conservation of angular momentum. So VA is going to be RP over RA times VP. RP was 0.586, the perihelion distance. This is 35, and we know that when it's close to the sun, it does 55 times 10 to the third. So this is 55 times 10 to the third. And from that, we get 0.586 divided by 35 times 55. We get 9.2 times 10 squared meters per second, or about 920 meters per second. So it slows down tremendously when it gets way out there. It's doing about 55,000 meters per second near the sun, and it's only doing 920 when it gets all the way out to the edge of the solar system. Something I didn't talk about that you may not know as well is our solar system kind of has this empty area where the sun and the planets all lie. And then beyond that is what's called the Kuiper belt. And it's a bunch of rocks, a bunch of large planetoids. Pluto's actually one of those objects that's out there. Halley's Comet's another, and it comes in, swings around the sun, and goes back out to that cloud. It's just a bunch of space rocks out there, and that's basically what Halley's Comet is. You'll be able to see it in your lifetime, hopefully. It's pretty cool, and you'll be able to tell people how to determine the eccentricity and how far out it goes, just from observing how close it gets to the sun and what its speed is when it gets there, and knowing its period. So pretty cool stuff. You only needed to know that it was orbiting in an ellipse, and you needed to know Kepler's laws to figure all this out, but it's a lot of information you can gather knowing very minimal stuff. So anyway, when we do a test or an exam or a quiz, this is typically what a Kepler orbit problem will look like. You'll be given a couple variables, usually 2 or 3, and have to assemble everything else from those few equations that we have. It's not too hard. It's really just plug and chug, but you need to know your equations, and you need to know how to interpret some of this stuff. But that's all good. So let's get back to talking about the force of gravity. And we only talked about 2 masses, or 2 point masses, last time. And we said that there was a force of gravity acting on each of them. If this is A and this is B, then the force of gravity on A due to B and the force of gravity on B due to A was G, mass of A, mass of B, times the distance from A to B squared. But there's a lot more that we need to talk about here. What if they aren't point masses. What do we do? And so, like all physics, one of the easiest things, one of the things that Newton actually realized and doesn't get talked about as much except among physicists, is that he realized that the force of gravity was subject to what is called the principle of supposition. And what that means is, if I have two masses, okay, so this is now my mass A, and I'm going to call for clarity this mass 1 and this mass 2. Let's say these lie on a at an angle, both of them are at an angle of 10 degrees from the plane. I know it doesn't, the arrows don't look quite like that, but how do we figure out the gravity on MA? How do we figure out if these two are stationary, what gravity MA feels? And the principle of supposition tells us that we don't have to worry about how these two influence each other. We only need to worry about how they are influencing the mass of interest. So the principle of supposition says that the force of gravity total acting on MA is the force of gravity on A due to 1 plus the force of gravity B, or on A, due to 2. You just add them together. It makes things super easy. Now look at what happens here though. We know that the force of gravity is acting, if I draw this, there is a force of gravity acting to pull this guy at 10 degrees. And that force of gravity, if this is 1 and this is our mass A, is G times MA times M1 over the distance from RA to R, or to 1 squared. Okay, let's say that these are L. I don't care what it is, but RA is going to be L. Now the force of gravity in the Y direction and the force of gravity in the X direction are our normal FG, sine of the angle, and FG cos of the angle. But look what happens when I add the forces in the X. So the forces in the X, this is FG in the X. This one also has FG in the X. If I add the ones in the Y, they completely cancel as long as M1 and M2 are equal and at the same angle away. That's really important. So the total force of gravity in the X, if M1 and M2 are equal, is simply G times M1 plus M2 times MA over R from A to 1 squared times cosine theta, and since there's 2 of them, we get 2 of them, right? Essentially, I need to get rid of that, I'm sorry. There's not 2 of them. I already accounted for the 2 when I added the masses here. But that is the total. There is no force in the Y, because the force in the Y from M1 and the force in the Y from M2 acting on MA cancel. Let's take another look at something. What happens when they're very far away from us? If they are very far away, essentially this angle goes to 0, and we know that cosine of the angle is 1 if we have very small angles. The small angle approximation tells us that. Typically for cosine less than about 10, you get around 1, around less than 10 degrees. So if we were very far away, what we would get is that the force of gravity was the force of gravity from M1 on MA times R all the way squared, plus the force from M2 on MA all the way, okay? And these would have cosine of theta, but theta is going to be very small, so we're going to effectively leave it off. So what this says is that all this mass, if they're very far away, acts like you have a mass 2m acting at their center of mass, pulling it, the object MA to it. That's really important. So far away, it acts like all mass at COM. When we get close up, so let's say we were close to a diamond-shaped pattern of masses, we would have to figure out the force of gravity due to each one, and they're all going to have different R's. You'll notice that if these were equal, you would have the Y cancel, but that's not necessarily true. So each of these masses would have their own R vector to MA, and each of them would have their own force vector to MA, and the total of those would be MA. The really nice thing is that we generally assume that things are far enough away that we can take them to be a point mass, but know that that's part of the problem that you're going to face next semester with charges. This is the exact same thing that's going to happen with charges. So imagine that you had a ring of mass and a little MA. You would have to integrate around this ring to find the total force of gravity acting. We're not going to do that in this class. For now, you just need to know that gravitational forces add the sum of them. They act as if none of these masses are interacting with each other. They're only interacting with the mass we care about. We can sum them up and figure them out from there. As I said, next semester, you're going to have the same thing in electrostatics. When charges are stationary, you can assume that they only act on the charge you care about and they don't act on each other. And it's something that you'll see next semester. Not too big of a deal right now, kind of a big deal next time or next semester because you have to integrate. Other than that, really the only takeaway is we can do a simple summation of all the masses. Turns out why that was historically important is when Newton wanted to know why an apple fell to the center of the earth, he assumed that he would have to figure out all the little masses of the earth that made up the sphere of the earth. And he realized he could sum them to get the total force of gravity. And he also realized that if the total force of gravity was the sum of each individual force of gravity, that the sum would become an integral, and that's how he invented calculus. The sum becomes an integral of the forces. This integral sign is actually a sum if you've never thought about that, but that's what it is. It's an infinite sum, or a sum of infinitesimals is kind of how we say it. That's not really important to you if you don't really care about the calculus so much, but this is why he had to develop calculus, was he was trying to sum a very large number of masses and to see what happened. So let's talk about a bigger problem. We already said that there are a couple reasons why Earth shouldn't work the way our simple model says it does. We said that we're going to assume that the Earth is a sphere, but we know it's not. It's actually kind of flat and smushed. We assumed that it had uniform density, and we're going to always assume that. And that's definitely not true. The core of the Earth is very different than the crust, and there's layers of mantle in there and stuff. And finally, we're going to assume, finally, the Earth is rotating. So we know it's rotating. And before, we didn't care that it was rotating. We assumed that it was just standing still, or we didn't need to worry about the rotation. So the fact that Earth isn't a sphere, we're going to ignore. We're going to treat Earth as a sphere. And the fact that it doesn't really have uniform density, we're going to assume it does. However, we're now, not right away, but soon we're going to consider the rotation of the Earth, and we're going to deal with it. We're going to add it to our equations, and we're going to see a few consequences of it, and that we can ignore a lot of it. but we'll talk about that in a minute. First things first, though, I have a problem, and that is, imagine, for simplicity's sake, that there were a tunnel that went all the way through the Earth. And I have a mass right at the surface, and it drops through that hole, passes through the center of mass, and out the other side, okay? Now, our equation for the force of gravity acting on this little mass, little m, and this is the mass of the Earth, is m of Earth over r between them squared. Your book talks about some sci-fi novel where they made an elevator that would shoot you to the other side of the moon, and the guy thought that you would accelerate super fast and go through to the other side. That guy did not understand math, is the main takeaway. So we're going to do some real math, some kind of cool real math here. I actually like this derivation. It's the first time I feel like we're doing something kind of useful with our derivations. So let's talk about this. If this force were the force of gravity inside the Earth, what would happen as we approach the center? We would see that our force, remember our force is ma, and that's m times g m m e over r squared. So once we approached the center, r would go to 0. And if r is going to 0, our acceleration is becoming infinite. So as the object falls, it's getting greater and greater and greater acceleration, and it just shoots out. It would go flying out the other end. We know from energy that can't happen, right? We know that mgh here, if we started from rest at the top of our surface, that we would have mgh starting from rest. Here we would have all mv squared because we would have no potential energy of gravity. And then when it shot out the other side, we would have negative, but we'd still have mgh. And it would come to rest. When it turned all this kinetic energy back into potential. We know that from our energy when we did free fall. As this thing jumps back and forth, it's just going to oscillate as long as nothing's slowing it down, like air friction or friction due to air resistance. So this can't possibly be right. This does not describe this energy here. So what are we supposed to do? And it turns out that if you think about this, okay, that as you fall, all the mass near you is going to be acting on you to try and pull you up, the mass as you pass. And so really, you're only going to get the rest of the mass. And what that turns out to mean is that the force of gravity only depends on, at some radial distance inside a sphere, it only depends on the mass inside here. This is the inside mass times your mass over r inside squared, okay? That's kind of weird. You're going to see this when you do electromagnetism. You're going to see this again. The electric field inside a charged conductor, if there's nothing inside it, there's no electric field inside it because it only depends on the charge inside. Same thing. So this is a preview to that. But here's our issue. What is M inside? Okay. So we assumed that the Earth had a uniform density, and uniform density is M over V. And that means that M inside has to be equal to V inside. And it turns out that V inside, we know for a sphere, is 4/3 pi r inside cubed times the mass inside. Or, and this V is 4/3 pi r squared. So this is equal to M over 4/3 pi big R, the radius of the Earth, squared, cubed. And from that, we can determine what m inside is. So m inside is simply, if I divide or multiply through by 4/3 pi r inside, I know that my 4/3 pi cancels. And what I get is I get m r inside cubed over r of the earth, the total r cubed. If I plug this in for m inside, so my mass is g times big M, m of the earth, I should say. Now r, I'm just going to put little r for that. This is r cubed over r squared, so it's just r over the radius of the earth cubed. So that ends up being that our force of gravity inside is m, whatever mass we care about, g times mass of the earth times r over the radius of the earth cubed. And does that work? Does that give us the appropriate force? So as we pass through the center, when r is equal to 0, we get 0. And when r is equal to the radius of the earth outside, we get that the force of gravity is equal to m g m e big R over r squared is just r squared. Okay? And that agrees with what we already know. It has to be 0 as it passes through the center of the earth, and then the force is equal to Newton's force of gravity when it reaches the surface. Past that, beyond surface, the force of gravity is simply m times g me times whatever our r happens to be, however far away we are. So what we say is that the force of gravity, if you're not used to seeing math equations written this way, this is just saying that we have different areas where the equation changes. They should meet at the boundaries, and obviously they do. So if r is less than or equal to r of the earth, we get that this is m g mass of the earth r over r of the earth cubed. And when it's r of the earth, so when r is equal to re, we get m g m e over r of the earth squared. And when it's beyond, when r is greater than r of the earth, we get mg mass of the earth over r squared. Okay, that's pretty fun. So just know that this is typically stuff you're going to be doing next semester with charges. Maybe get used to doing this stuff. It's getting a lot closer to upper division physics, having to figure out lots of little geometry and tricks and stuff, tricks with the algebra. But this is actually a pretty useful idea because it's why this elevator wouldn't work. Another thing that we're going to talk about in a couple weeks that I should note is as this thing goes through the earth and comes back up, like I said, it's as long as there's no force of drag, no friction slowing this down, this thing will oscillate. And it'll actually oscillate just like a mass on a spring. That's because a mass on a spring and gravity act as central forces. And so we could actually treat this like a mass on a spring where the force is minus kx, which is minus kr. And that would be the same thing as our gravity. Our gravity force would be minus gmm r over r of the earth cubed inside. And so you could solve this for the energy and a bunch of other stuff that we're not going to do right now. But gravity is a central force, meaning it's always got this negative sign that brings the force is always trying to restore or bring the other mass back to the center mass of gravity. That's for much later. We'll talk about that when we do chapter 15. We might not talk about it in this sense, but we'll talk about restoring forces and central forces. But you can keep that in mind, that if you did dig a hole through the earth and there was no air drag, the object would just oscillate. It would go from one end to the other, back and forth, exchanging potential energy and kinetic energy at every part of the path. All right. So let's talk about an object on the surface of the Earth. And I want to mention one quick thing. So imagine this thing's actually rotating at the equator, but it's a box, or you're at the equator. And so the Earth is rotating with omega. If you were at the pole, this wouldn't happen because you could say that it's not rotating at the pole. But let's imagine you're on the surface. So you, if I look from above, you as you stand here are going around with some speed omega. And we're going to assume that the Earth is circular here. Okay. So what we want to know is, what is the force acting on your body? What is your weight actually? So we know that when you rotate around, you have this A rad, right? And you also have gravity pulling you down. You have A rad because you're going around. Remember that A rad was equal to V squared over R. And if omega R is V, then this becomes omega squared R. And if we multiply both sides by M, we get that this is the force of radial acceleration. We know the force of gravity will be G M of the Earth times M over R squared. This is the force of gravity. So if we draw a free body diagram, we have force of gravity, we have the force radial, and we have some normal force pulling up. And this normal force is actually the weight that we see on, say, a scale. So we want to determine what this is and how much it is affected by the rotation of the Earth. Okay. Now the Earth rotates through 2 pi rads in 86,400 seconds, the number of seconds in a day. That means that Earth has an angular speed of 86,400, 2 times pi divided by 86,400 of 7.27 times 10 to the minus 5 rads per second. All right, if we look at this equation, we get that m a rad is equal to the force of gravity minus the normal force, and we want to find the normal force. So we want to find N is equal to Fg minus ma rad, which means that the force of gravity is m times g times m of the Earth over r squared minus m omega squared r. And for simplicity, we're going to say that the mass is 40 kilograms. But here, we want to really, we already know this. This was m times 9.81, we can assume. But what is this if the radius of the Earth is 6.388 times 10 to the 6th meters? Okay, so we want to know what this becomes, how big this is, and is this something we should worry about? This is essentially about 400 newtons. How big is this centripetal force? Well, I can see that this would be 40 times 7.3 times 10 to the minus 5 squared times 6.388 times 10 to the 6 meters. If I do this math, I get, let me actually do it right here. So I get that m omega squared r is equal to 40 times 7.3 times 6.388, 10 to the minus 5 times squared, times 10 to the minus 5 is 10 to the minus 10. So this whole thing is going to be times 10 to the minus 4. 40 times 7.3 times 7.3 times 6.388, I get 13.6 times 10 to the minus 4. So I get 1.36 times, I get 1.36. Which seems like I've got something kind of weird going on there. Let me double check myself. Oh, no, I know what's happening. This is 1.6 newtons, okay? So your weight is 400 newtons and it's getting changed by the radial acceleration is actually only taking away 1 newton. The actual acceleration, omega squared r, if we divide this by your 40, so divide 1.36 by 40, and I get 0.34 rads per second squared. And just bear in mind that 9.81 meter per second, if I divide by 2 pi r, I'm not going to turn that into, if our r is 6.38, so 9.81 times 6.388, I'm sorry, 9.81 divided by 6.388 is 1.5 times 10 to the minus 6-ish, would be the angular acceleration. So I want to talk about this a little bit more though, kind of what's going on here. New slide. So as the object goes around, rotates around, okay, as we said, we have this ma rad, and that's actually the net force. Where we used to write ma, we're going to write ma rad. And it's got some normal force because it's sitting on the surface of the Earth, and it has some force of gravity, right? So ma rad is down, normal force up, force of gravity down. Okay. And ma rad is really m omega squared r. And this is your radial acceleration. That is actually the Coriolis force. It's the force due to the fact that the Earth is rotating. It's the acceleration due to the fact that the Earth is rotating. So what actually happens is in the northern hemisphere, it causes a weird deflection because it's rotating. Imagine you were at the top of a very tall building and you dropped a coin. The coin would actually land at a different spot because the Earth is rotating below the coin. This is also responsible for water flowing the opposite way, and for clouds moving the opposite ways. It's because of the rotation of the Earth. As far as we're concerned, this is so small compared to gm m over r squared that we almost never have to worry about it. But the further away you get, the more important this becomes, and the less important gravity. So for satellites very far out, where r is very big, but r is small, you can see that we would end up caring more and more and more about the angular velocity and the angular acceleration and ARAD, all that good stuff. Okay. It's not super important, but it's something to keep in mind. It's something you will study in engineering. You'll study in more advanced physics, how the Coriolis force works and accounting for it. It becomes very important for things like artillery shells. Anything that goes up really high and comes back down, you actually have to account for this rotation of the Earth. In general, at the surface of the Earth, we don't really need to worry about it. So from that principle, we can develop another principle, and that is that a satellite that's like sending you your TV at home and is rotating at a distance r of the Earth plus r above the Earth. So if we say that it was 2 kilometers above the Earth, what we actually mean is that r of the Earth is 6.388 times 10 to the 6 meters, and little r is 2 times 10 to the third meters. So we'd have to adjust this, and basically our r would be our Earth plus r, which would be 6.39 times 10 to the 6 meters. Okay, so a satellite is at 2 kilometers above the Earth, or a distance of 6.39 times 10 to the 6 meters. And what we want to know is, we already know the force on it up there is equal to those things, but there's no normal force, right? So it should be falling back. So how does it stay? Well, it turns out that m omega squared r is equal to g m over r squared. That's all well and good, but that doesn't really help us much. What we can, however, do is actually explore this with energy, because we know that when it's rotating, it has I omega squared over 2. So the energy at any point has to be this kinetic energy of rotation. And if you recall from last lesson that there was some potential energy of gravity, right? And that potential energy of gravity is minus g m little m over r, right? So this is our total energy of rotation and gravity at any time. We're going to say that that is I omega, but I'm going to come back to that, g m over r. I didn't put squared, right? Right. This is the potential energy of gravity. So I omega squared over 2, remember that I for a point mass, and we're going to assume this is a point mass, is m r squared. So this becomes m r squared over 2. If we assume that omega is v over r, we're rolling without slipping, so we assume the satellite's in some circular orbit, then this becomes v squared over r squared, or mv squared over 2. That's all well and good. That's our normal kinetic energy. However, we can do one step better. Assuming that m omega squared r is our angular velocity, or I mean our ARAD, our centripetal force, we know that this is equal to mv squared over r. This is ARAD, this is ARAD, right? So if mv squared over r is equal to that, right? How do we turn that into something usable? Something slightly better, something slightly more usable. And it turns out that this is actually, if we put this in terms of the gravity, A of the gravity was g, big M over m, r squared, right? I'm sorry, that is not true. That is true. So this becomes m times g, m of the Earth over r squared, right? And we can cancel these m's. And so what we get is we get that v squared is equal to g m of the Earth over r squared, or over r. That's just canceling the little mass, moving this over. So mv squared over 2, our kinetic energy, is little m times g times m of the Earth over 2 times r. Multiply top and bottom, or multiply the bottom by a half, multiply by a half, multiply by m. So we see that this becomes g m over 2r. I'm going to put this on its own slide. This is the important equation. So E at some R, at any R, is G M M over 2R minus G M M over R. If I multiply by top and bottom by 2 so that I get the denominators the same, I see that this actually ends up being minus G M M over R half. I can equate sometimes R to A, some semi-major axis. We usually do that. So E at any A would be minus G M of whatever you're rotating around over 2A. Another way of saying that is, notice this is U over 2. It's the potential energy of gravity. That was minus G M M over R. So it's U over 2, or it's minus the kinetic energy. But the energy at any time. So if you know the energy at any time, you know the kinetic energy, and you know the potential energy at any time, assuming that you know R. And this works like any energy. We're going to see that in a minute, but let's say we move a satellite from a mile above the Earth to 5 miles above the Earth. We could figure out what the total energy was before, and then find the potential energy, and then find the kinetic energy and how fast it would have to rotate out there. It's not too bad. We're actually going to do a problem at the very end of this whole lecture where we're going to use this for a spaceship. It's actually one of the problems in the book. But I want to talk about escape velocity next. So I'm just going to do a satellite coming to Earth, crashing into the Earth, just to show you how this energy works. And then we'll do another problem at the very end. So imagine we have this satellite that was at an original radius of, let's say it's at 10,000 kilometers. So it's at 10 times 10 to the 6 meters initially. And we're going to bring it down from there. So it's going to, our final is going to be R of the Earth, which is 6.388 times 10 to the 6 M. So initially it's up here somewhere, and we're going to let it come crashing in. Okay. So we want to know what is V final when it hits the ground. So we start off saying that the energy at any point, as we said, was not only just GMM of the satellite over R, or RA squared, not squared, over RA with a 2 minus G M of the Earth, mass of the satellite, over R. This is our kinetic, this is our potential, but that whole thing becomes, and I don't know why I wrote that. Oh yeah, I do. R initial. But I don't want to do that. So this becomes minus G, mass of the Earth, mass of the satellite, over 2 R with a minus sign. We can easily compute that if that's R naught. So the energy at initially is minus 6.673 times 10 to the minus 11. Mass of the Earth is 5.97 or 98, depending on what you want to use. I'm used to using 5.97. Let's say that this satellite is only a little cube satellite, a 2 kilogram cube satellite. So this is 2. And initially we said it was at 10,000 kilometers, which is 2 times 10 times 10 to the 6th. And we can see that this ends up being 24 minus 13 minus 11. 13 divided by 6 is 7. So something times 10 to the 7th. 6.67 times 5.97 times 2 divided by 20. And I get 3.98 times 10 to the 7 joules with a negative sign. Okay. And then I want to know what the final energy is. So how do we find the final energy? Well, we know that at the final energy, R is going to be R of the Earth. So R final is R of the Earth, which is 6.388 times 10 to the 6th meters. We just found that the energy initially was minus 3.98 times 10 to the 7th joules, right? So what is the final energy and how does that give us the final velocity? So remember that this final energy will be mv squared over 2 minus gmm over r final, the potential energy of gravity at r final. And because E initial is equal to E final, let's actually find this number first. Potential energy final is minus gmm over R final, which is equal to 6.673 times 5.97 times 20, did we say? Or 2? We said 2. Divided by 6.388. And I get 12.47. This was to the 11, 24, so 13 over 6 times 10 to the 7. That seems wrong. So this is minus 11, 24 over 6. So this becomes, oh no, it's right. I'm sorry. I was just losing my mind for a second. Joules. So the final potential energy when it hits the Earth is going to be negative 12.47 times 10 to the 7th joules. So let's see if we can find this mv squared. Noting that E initial is equal to E final, we get minus 3.98 times 10 to the 7th joules is equal to mv squared over 2 minus 12.47 times 10 to the 7th joules, right? Solving this for mv squared and noting that m is 2 over 2. So really we're going to solve this for v squared. We get that 12.47 minus 3.98 times 10 to the 7th. This moves over. And so this becomes 8.49. 8.49 times 10 to the 7th. When you're doing these, I usually move it one way or the other. This is equivalent to 84.9 times 10 to the 6th, right? And then when you take the square root, this just becomes 10 to the 3rd. So what is the square root of 84.9? I get 9. So I get that V is 9 times 10 to the 3rd meters per second, or 9,000 meters per second. I can find out what the original speed was, but this is the final speed. And all I did was I set this initial energy to mv squared minus the potential energy of gravity. That's how it works. It should have sped up. We'll figure that out right now as a way of kind of making sure that we're right. Remember that the total energy at any time at any r is minus gm over 2r, okay? And when r was 10,000 kilometers, which is 10 times 10 to the 6 meters, we want to know what the velocity was. So we know that this energy at r is equal to the kinetic energy mv squared over 2 plus minus gm over r. So what is this? Minus gm over r. Satellite was 2. We can find that again. 6.673 times 5.97 times 2 divided by 10, I get 7.9. This would be 7. This is minus 7.97 times 10 to the 7th joules. What did we get before? That it was only 3.8. So we could figure that out right now. But that is our potential energy. This is 7.97 times 10 to the 7th joules. We know that our total energy from back here was negative 3.98. So ER is equal to 3.98 with a negative sign times 10 to the 7th joules, which is equal to mv squared over 2 minus 7.97 times 10 to the 7th joules. Moving this over, solving for v squared. So this was our initial, was the square root, m was 2 over 2, so nothing. 7.97 minus 7.97 minus 3.98, all times 10 to the 7th. This gives us 4 point, a little bit less actually, 3.99. So if I go the square root of 39.9, this should have been 3.99 times 10 to the 6th. This is times 10 to the 3rd. And the square root of 39.9 is 6.3. So this is 6.3 times 10 to the 3rd meters per second. So our initial speed of the satellite was 6,300 meters per second. Should it have sped up as it fell to Earth? As it falls towards the Earth, gravity is going to do positive work in the direction of the force of gravity, and it should speed up. And we found that our final velocity was 9,000 meters per second, which is good. Something could have been really, really wrong if that wasn't, didn't work out. But mainly this problem is just understanding how you can use the total energy at any time, separate that out into 2 separate kinetic energy and potential energy, and do that at any time to solve v squared. Not too hard. Let me write those on their own blank slide though. So the energy at any time, is the kinetic energy, mv squared over 2, plus the potential energy of gravity, gm. Note these are our little m's. This is the m causes gravity. So it's the force of gravity is m, is the force acting on m due to big M. But this is the potential, okay? And this is equal to gmm, again, big M, over 2r minus gmm over r, which again gives us that E at any time is gmm over 2r. And setting these two things equal, or setting these two things equal, will give you usually what you need. And then by conservation of energy, now something we haven't really talked about, but we knew it from before, the force of gravity is conservative. And that means that we don't care about the path. That means that as this satellite is up here, it can kind of go down and come back up, go down and come back up. And all we really care about is its initial R and its final R. Gravity is a conservative force. So the energy initial is equal to the energy final as long as gravity is the only force acting. It's a conservative force, and therefore we just write down these equations. We don't have to integrate. We don't have to do anything like that. And we get this, okay? Alrighty. that's a little bit weird because um, what's going to happen here is that's basically going to say that G mm over 2r has to be equal to G mm over 2r initial r final. Um, so that doesn't appear to make sense um, to reconcile that. But what we simply do is we find the energy and we use it to solve for both of these quantities. And that will definitely be true. Strangely enough. Okay, one last thing I'm going to say about this is the part that's always bothered me. It's the part where I mess these things up. Um, but one last thing I'm going to say is that we've assumed, okay, that there's some speed. But what if an object was traveling faster than the Earth above the Earth, right? So if it was traveling faster, it would have a little bit different energy because this would actually be greater. So if it had greater energy and it fell, you could figure this same stuff out. This part isn't necessarily going to work out. But regardless. But when an object is traveling really fast around the Earth, in order for it to leave the Earth and fall into the sun, let's say, it would have to slow down. So it would have to have a negative V equal to its rotation about the Earth to fall. And this, it turns out, is a kind of cool problem that hopefully you'll see at some point, where if you want to shoot something into the sun, it's actually really hard. You have to slow down V enough that it follows a trajectory that bounces it into the sun. It's actually easier to give it a little bit of a boost and it will follow a trajectory that leaves the solar system. So it would be better if we want to get rid of trash to shoot it out of the solar system than to try to shoot it into the sun. That's weird, but it's because your rotational energy is so great that you have to turn that into potential somehow. And how you would do that is slowing it down and causing your object to gain to fall more towards the sun. Anyway, this stuff gets really super confusing. The only thing you need to know is that the energy at any time is this, and that's equal to this energy here. Okay. One last thing I should note is that when we do planetary orbits, remember that the E, I'm going to put a new slide actually, for an elliptical orbit at A and at P, the energy at A is equal to the energy at P, and that means that G M M over 2 RA minus G M M over RA is equal to G M M over RP minus G M M over RP. But a better way to see this is that this is M VA squared over 2 minus G M M, that's the mass of the Earth, RA is equal to MV P squared over 2 minus G M M over RP. All right, first of all, if we get rid of those M's, we see that VA squared minus, and multiply through by 2G M of the Earth over RA is equal to VP minus 2GM over RP. And we could put in that RA is equal to RP VP over VA. So you could put in this is in terms of VP and VA, and this is in terms of VA and VP. You could do some fun stuff with this equation, but the net thing at the end of the day is that essentially, if you remember that this was Kepler's second law, you can use Kepler's second law, or you could use this to determine the velocity and radius of the aphelion distance or the perihelion distance. Why do I keep doing that? I'm sorry. This is actually a perihelion. This is an aphelion. I keep wanting to write A because it's closest to the sun, and I'm thinking A and B. Anyway, so you can use energy to find VA if you knew RA, VP, and RP. Or you could use this equation, which is a lot easier, but they should both give you the same. Anyway, so last two things I want to talk about. The last real mathematical thing I want to talk about is escape velocity. And so knowing this, that if the energy is the kinetic energy plus the potential energy at some point R, okay, imagine that there's a oxygen atom at the surface of the Earth, or an astronaut getting launched into space at the surface of the Earth. We know that when he gets very far away, or the particle gets very far away, when R is very big, right? We said that the potential energy should go to zero, and we assume that all of the kinetic energy is spent. Okay, so all of the kinetic energy also goes to zero. It's fighting gravity all the way, so it's losing kinetic energy, and it's also, the potential energy is becoming zero. So if we write our initial energy is equal to our final energy, and we know that our final energy has to be zero. When it gets so far away that it's no longer moving and it has no potential energy, what happens? So E initial from before was mv squared over 2 plus negative g m of the Earth, m or m of whatever we're rotating, over r. If I say this is zero, because it's equal to E final, I see that I get v squared is equal, cancel the little m's, is equal to 2 times g times mass of the Earth over r, or that v is 2 times g times mass of whatever we're rotating around. I called it the Earth there, but this is known as the escape velocity from a planet. You get it by, as I said, setting the potential energy going to zero and the kinetic energy going to zero when it's in some final position far away. So let's look at what the escape velocity is for a couple of things. For the Earth, v is square root of 2 times g times mass of the Earth over the radius of the Earth. This ends up being 2 times 6.673 times 5.97 divided by 6.388. I get 12.47. This was negative 11. This was 24, so 13 over 6, so times 10 to the 7th. If I back that up 1, this is the same thing as 1 square root of 1.247 times 10 to the 8th. Square root of 10 to the 8th is 10 to the 4th. Square root of 1.247 is 1.12 meters per second. And I'll talk about this in a minute, but this was Earth. For Jupiter, Jupiter actually has a mass of Sorry, I don't know where I put it. Oh, 1.9 times 10 to the 27 kilograms. And the radius of Jupiter is kind of hard to say. Jupiter is actually a gas giant, so where the surface is and where the atmosphere ends, but we generally take it to be 7 times 10 to the 7th meters. So the escape velocity of Jupiter is 2g mass of Jupiter over r of Jupiter, which is, if I do that from below, 2 times 6.673 times 1.9 divided by 7, I get 3.6. This is, g is negative 11, so 16 divided by 7 times 10 to the 9th. Let's move that back, and we see that this is the square root of 36 over the square root of 10 to the 8th times 10 to the 4th meters per second, which is 6 times 10 to the 4th meters per second, or 60,000 meters per second. For the Earth, it's 11,000 meters per second. For Jupiter, it's 60. And lastly, I want to talk about the moon. So the escape velocity from the moon, okay, would be, the moon has a mass of only 7.36. 7.36 times 10 to the 22nd kilograms, and the radius of the moon is a paltry 1.74 times 10 to the 6 meters. Putting these numbers in to 2g mass of the moon over r of the moon, I get 2 times 6.673 times 7.36 divided by 1.74. So I get 56.45. This is to the minus 11, 22. So 11 over 6, this is times 10 to the 5th. If I back that up, this is square root of 5.645 times 10 to the 3rd meters per second. Square root of 5.645 is 2.4, let's call it. So V of the moon is 2.4 times 10 to the 3rd meters per second. All right, so Jupiter was 60,000, the Earth was 11.2 thousand, and the moon was 2,400. So V of Earth, V of Jupiter, and V of the moon. 60,000 meters per second, 11.2 thousand meters per second, and a paltry 2,400 meters per second. Those of you in chemistry, okay, know that the root mean square speed is basically the average speed. And for hydrogen, it's 2.4 times 10 to the 3rd meter per second for H. And for oxygen, it's about 539.2 times 10, no, not times 10, meters per second. This is actually at around 100 Celsius, but, and I think hydrogen, that number is actually higher. I think it's like 190 degrees. Regardless, these are the root mean squared. That means that if you have a, like a room full of hydrogen, the mean speed is 2.4, well, the root mean squared speed is 2.4 times 10 to the 3rd, or 2,400 meters per second. And if you had a room full of oxygen at 100 degrees Celsius, the mean speed, or the average speed of a molecule is 539.2. Now, if the escape speed from the Earth is 11,200 meters per second, that means an object going faster than that will get away forever. So if I'm on Earth and I launch at 600 meters per second, I'll never get away. Earth gravity will pull me back. However, if I launch at 11,201 meters per second, I will get away forever. If my initial velocity is 11,201 meters per second, I'm gone. So things that need to be launched into space have to be launched fast enough to get away from the Earth's gravity. Okay, and you might look at this and go, well, I'm going to tell you, you may not think it, but the Earth actually doesn't have a lot of oxygen or hydrogen. It has a little bit, but not a lot. You might say, well, how can that be? Hydrogen only has a root mean square speed of 2,400 meters per second. Well, that's the root speed. And so this looks like some kind of bell curve of root mean speed for each hydrogen atom. And most of them are going to be at this 2,400 meters per second, but some of them are going to be much slower, and some of them are going to be much faster. So a small percentage of them will be going greater than, let's say, 12K meters per second. And over time, you're going to lose your hydrogen. It's very, very possible for a hydrogen atom to go fast enough to get away from the Earth, even though its average speed is only 2,400. Secondly, we do have oxygen here. Oxygen has a really low root mean square speed. It's a heavy particle consisting of a much heavier atomic nucleus. But again, you could have some oxygen that's reaching 11,200 meters per second on Earth and getting away into space and never coming back. The reason why the moon is pretty much devoid of any atmosphere is exactly that. The moon has an escape speed we found of 2,400 meters per second, which is precisely hydrogen, which means hydrogen can't stay on the Earth or on the moon. It floats away into space, most of it immediately. Jupiter, however, has an escape speed of 60,000 meters per second, and almost nothing gets away. Hydrogen's the lightest gas. It should go the fastest. The root mean square speed of hydrogen, of all hydrogen atoms, so the average speed is basically 2,400 meters per second. How many of those are going to be doing 60,000 meters per second? Virtually none. And that's why it turns out that Jupiter is what's called a gas giant made of hydrogen. So is Saturn. They can't escape. The sun is made of hydrogen because the hydrogen can't get away. But the Earth and the moon and Mars and all the other planets that don't have a lot of hydrogen, they lost it because they didn't have enough gravity to keep the hydrogen on the surface of the planet. Over time, the particles just would go fast enough that they would fly away into space. Kind of cool to think about it that way, where we may have an atmosphere with a bunch of water, but really it's not that much. Very little hydrogen compared to something like Jupiter. And it's because the Earth is just barely big enough to retain enough oxygen and hydrogen and nitrogen to let us live. And then the really big planets are all hydrogen, Saturn and Jupiter, or all nitrogen, Uranus and Neptune. Okay, but that's root mean square. The only thing you need to remember is that the root or the escape velocity of some mass, you have to be doing that, where r is the radius of the mass. That's the escape speed. And the only other thing, I guess, is that Root mean square is basically the average. Particles go much faster, even though the average speed of all particles is pretty slow. They go fast enough to get away from the Earth over time. Okay, so the very last thing I'm going to talk about, the last thing that your book talks about is, oh no, before we do that, we're going to do this problem because I want to show you how we can use some of the concepts with Kepler to do a problem. This problem is in your book. You can go step by step through it in your book. This is a circular orbit becomes elliptical. So imagine you have a spaceship with a mass of 4.5 times 10 to the 3 kilograms, and it's at a distance from the center of the Earth of 8 times 10 to the 6 meters. It's in a circular orbit, and the period is 7.119 times 10 to the 3rd seconds. Now, at that point, it's got some energy. We're going to figure that out. But this thing breaks. So originally, it was floating around in a circle. And when it breaks, it suddenly gets itself in this elliptical orbit where essentially this thing is no longer, the planet's no longer at the center of a circle, it's at the foci of some ellipse. And we want to know what the new period for the spaceship is. That's what's going on here. So in order to do this, we need to do a couple things. Number one, we need to find the energy. Essentially, what we're trying to find is we're going to find T. And we know that T squared, T final, I should say, but we know that T squared final will be equal to 4 pi squared gm of the Earth, what you're rotating around, times A final cubed. So how do I find A final cubed? And to find A final cubed, I know my energy at A final will be minus gm of the Earth, m of the rocket, over 2 times A final. And because of that, I can solve this as A final has to be minus gm E times m over 2 times the energy final. But what is the energy final equal to? And the energy final is equal to mv final squared over 2 minus gm of the Earth m over A final. A final. No, don't do that. Okay. And this, it turns out that A final do I want to do it that way? So the initial energy, no, that's fine. I'm good. So here, all right, I need to find my V final. But V final, remember, was 0.9696% of V initial. And V initial, okay, if we come back to here, we don't know what V initial is, but it turns out we do. So if we know the period, V is going to be equal to the distance over time, right? But the period is 1 rotation. So this is going to be essentially how far around it went, or 2 pi times r, the original r initial, divided by the period. That is our V initial, our initial period, right? So knowing that, let's plug that in here with the 0.96. So we get that m over 2 is equal to 0.96 times 2 pi r initial over t initial, okay, minus g m of the earth times m over a final, right? And that energy is what I'm going to tuck in here. But we know that this A final at first, this is not actually A final. This is R. Okay. I'm sorry, I was being crazy. Initially, before it starts to move out, we know that right when it hits its brakes, it's still at R. So this becomes that, and that becomes that. And for clarity, I'm going to rewrite that all right here. So we have that E final is mv squared final over 2 plus negative g m of Earth over r, the r that the spaceship is originally at. Secondly, we know that the energy final is gmm over 2a with a minus sign. That's the energy at any time. So we know that this energy, we can find A final as minus g m over 2 E final. But V final is 0.96 of V naught, which is 0.96 of 2 pi r over t that we were given. And then the last thing, we're going to have that t final squared is equal to 4 pi squared gm of Earth times a final cubed. So let's get to work on this stuff. V initial, if we go back and look, V initial was 2 times pi times actually, let me go back to here. Save us a lot of time of staring at stuff. This becomes, this whole thing up here becomes, I had this written in some weird way. So what I'm going to do is I'm going to write this as, eventually, if you find A final is equal to minus g m of the Earth over m divided by 2 times the energy final, which is m over 2 times 0.96 times 2 pi r initial over t initial squared minus g m over r initial. If you do that, what you find is you get 7.418 times 10 to the 6th meters. Once you have that, if you plug that in and solve 4 pi squared over gm over a final cubed, you get that this is 106 minutes. Okay. just a bunch of tedious math I don't want to do. But so from this guy here, which is just the energy at any time for A, the semi-major axis final, you plug in this E final at the bottom, but in order to find V final, you have to multiply the initial velocity by 0.96, and the initial velocity in that question you have to find by taking the circumference over the period, how far around it went, divided by the period, and because it's a circle, you know that, okay? This is actually a big pain in the butt question because of A and R, and making sure your A's and R's are not messed up. It's easy to assume that A should be R, but it's not, because where it's initially at, and I'll explain that, in a circular orbit, it would initially be at R, and then even though this is maybe R, this becomes A. I don't know where it's at, but let's say this R, because it slows down, my guess would be if it's slowing down, it's probably actually going to be out here, but whatever. Basically, your distance, though, to the Earth is going to change. So you've got to figure that out. And your semi-major axis is going to change everything. Yeah, that's all fun. It's in your book. It's online. You can read that problem. Problem's kind of a pain. So the final thing I want to talk about is what is actually going on. I don't know if we ever talked about gravity, if I ever asked you, but gravity is one of the things that people assume they know, but they just kind of take for granted. I mean, why should an object fall out of your hand and hit the ground? Why should the Earth pull any mass towards it? Why would that happen? For a long time, they've searched for something called a graviton, and essentially what that's explanation of that is that you can't have force at a distance. If M1 is doing something to M2 that is making M2 accelerate in some direction, then there must be some particles that are traveling from M1 to M2 and telling M2 to go that way, or making M2 go that way. So the reason there was something called a graviton that must be traveling from one mass to the other and somehow causing gravity, the force of gravity. Einstein came along, and Einstein realized that gravity actually is something called the curvature of time and space. And what that means is you can imagine, and this is a really bad example, you can imagine two balls on a bed. And if this ball were really, really heavy, it's going to cause the blanket on the bed to sink down. And that is going to cause the actual surface, much like when you go around the Earth, you travel what you think is a straight line, but you're actually going in a circle. This particle, if it tried to on an overhead view, okay, this is a heavy mass. This lighter mass tries to shoot past it, and what happens is it ends up getting curved around this mass. And so what Einstein explained is that mass actually causes space and time to curve around itself. And the more mass you have, the stronger the curve. And that bending of space-time is a lot like, so little mass, bigger mass, right? Really big mass like a black hole. And anything that gets too close to the black hole gets sucked in and can't get away. So essentially what's happening is we live in a four-dimensional world We, however, only see things. We generally actually only see things in 2 dimensions, or think about things, analyze things in 2 dimensions. And the 4-dimensional space-time, all combined, is being curved, and we see that as gravity, okay? There's a lot of cool things that they've done. They've found gravity waves. Gravity is affected by a lot of things. There's things like the cosmological constant, things beyond this course. There's a lot of relativistic effects. And essentially, if you only remember that gravity is really the curvature of space-time, and basically really big masses bend space-time a lot, little masses bend it a little bit. It's a nice way to understand gravity. The math is very complex. Tensor analysis, which are even more complex than matrices. I urge you to read up about it. Read things like any Stephen Hawking's book will go into it. But as far as us, there's not a lot we can do with that. We just don't have the math at this level to handle these problems. Not a lot of people do. If it's something you enjoy, you can go to grad school and study astronomy and study astrophysics. But yeah, anyway, next time, next week, we're going to go through and start doing fluids, Bernoulli's principle and Bernoulli's equation and Archimedes principle. So anyway, hope you stay healthy. I'll see you later.